Okay, so we have been through all of the observations that we've made about our solar system over the past semester, and they come down to disk shape and planetary types and space debris and a common age for the solar system. Now we have to put those observations that we've made into a hypothesis, just like we do in labs all the time. We come up with an observation, we think about the research behind it, and then we look for the hypothesis to explain this. If our hypothesis is supported by data, it becomes a theory after time has proven that that data really does support the hypothesis. So we have a lot of people who have been looking at a lot of data in regard to these observations, and they've come up with some theories, and that's what we're going to start to look into now. And you will find as we go through these theories that there's not one right answer for all of these characteristics. And you can make up your own mind, and you can think about how you would add some data to these hypotheses in order to see one theory that might explain the entire origin of the solar system. But in terms of these, we have one of the earliest theories called the solar nebula theory. We're going to be talking about that at length. It tends to explain the disk shape of our solar system. It also tends to explain the common age, right at about 4.5 billion years of our solar system. So we're going to go into that first. We have a lot of theories in regard to planetary types and terrestrial versus Jovian planets. We have some theories on space debris and asteroids and meteors and comets and dwarf planets. And of course, we have another theory on common age. But let's get to the solar nebula theory first. So the solar nebula theory says that after the universe formed, there was a lot of gas in the universe, and a cloud of gas is called a nebula. So there were many clouds and many nebulas in the universe, in fact, millions of them. The one that is home for us and our solar system came to have areas of high pressure for dust and low pressure for dust in this cloud of dust. Not everything was equal in that cloud. And because of the law of equilibrium, that dust wanted to even out in its pressure. So it moved from high pressure to low pressure to even itself out. So in doing that, it happened to be a counterclockwise turn. And after that counterclockwise turn started, and after equilibrium was moving along and we were moving toward equilibrium pressures, then Newton's first law kicks in, and that says that a body in motion tends to stay in motion. So this nebula that was destined to become our solar system began its counterclockwise rotation, and there was nothing stopping it. And in addition to that, as that happened, that also started to move the pressures into the center and start a contraction. That contraction was fueled by gravitation, that F equals ma, force of gravitation equals mass times acceleration. And remember, acceleration is not just speed, acceleration is direction. So as this started to rotate in a counterclockwise direction, it started to have acceleration with that, and that's when gravity started. So we have a rotating and contracting cloud or nebula. And at this point, it's got equilibrium pressure. It's moving along. And as it's contracting, it's not in equilibrium then. It is contracting at different speeds. And, for every action contracting in, there's a reaction pushing out, Well, that pushing out seemed to go in different directions. And you see with the two there, what I'm pointing out to you is that there was pushing out that went up and that went down and in different directions. Well, everything actually canceled out to a direction that was perpendicular to the axis of rotation. So in other words, this is rotating counterclockwise around an axis that is right about here. And when those pushing out motions go up and down, and they're going up and they're going down, they cancel out right perpendicular to the axis of rotation. This is known as a protoplanetary disk that forms in solar systems perpendicular to the axis. And this is the equatorial plane that became our ecliptic. Now you might ask why this is happening perpendicular to the axis of rotation. This is actually very similar to a skater who is turning on the conservation of angular momentum. So this scientific law, the conservation of angular momentum, says that as her skirt, if you watch her skirt going up and down and up and down, when she is spinning fastest, that skirt actually becomes perpendicular to her axis of rotation, which is up and down for her axis of rotation. Her skirt is perpendicular to it when it is rotating quickly. And so everything cancels out for the up and down fluttering of her skirt and becomes an equatorial plane. This is known as the conservation of angular momentum. You also see it in pizza tosses. And when you have an experienced pizza maker, he will toss the dough so that it goes up and it goes down. He tosses it at an angle because he knows when it reaches the top of its rotation, it will flatten out. And the fluttering of the pizza dough, the up and down motion of the pizza dough, will become a equatorial plane at the top of the toss. This is the conservation of angular momentum. So if you want to think about a skater's skirt, go for it. If you want to think about a pizza dough at the top of its toss, you can think about it again. You can think about that as well, conservation angular momentum. If you want to remember this for the rest of your life, you can think about it. You know, conservation of energy. Energy is not created or destroyed, only transferred. And you know, conservation of mass. Mass is not created or destroyed, but it's transferred. You got conservation of angular momentum. Spinning is not created or destroyed. It's transferred to the plane that is perpendicular to the axis of rotation. Okay, so you can think about conservation of energy, mass, and spinning. When we look at our theory of the solar nebula theory that is making that disk shape that comes into play for not only our ecliptic in the solar system, but also our common counterclockwise rotation and our common counterclockwise revolution around the sun, with the exception of Venus. You can also point out, although it is controversial, that the solar nebula theory comes up with a common age for the Earth, Moon, and meteorites, that everything formed at the same time, that the sun and the gas and the disk shape, the protoplanetary disk, formed at the same time. That's why we see that 4.5 billion year age in magma from the center of the Earth, from volcanoes, from moon rocks at 4 billion years, and from meteorites like the one that struck Siberia in 2013, was also aged to 4.5 billion years. So you could look at the solar nebula theory for the common age as well, but it is controversial, and we will get back to that in a bit. like I said, the solar nebula theory talks about the fact that the planets formed along with the sun, and that the planets grow from the gas and the dust in the disk, and they're left behind when the protoplanetary disk clears from the solar wind from this sun that has now become luminous. Remember, there's no luminous sun here. There's really no luminous sun here. It takes billions of years for the sun to light up. So we've got a theory that we talked about, solar nebula theory for the disk shape and for the common age. But the solar nebula theory had nothing to say about planetary types and had nothing to say really about space debris. No. Maybe it talked a little bit about, stuff that was left over in the gas, but nothing too specific. We need more theories for that. So let's get to some really specific theories for that on the next video.